Hey everybody. Today we're doing a short review of right triangle trigonometry. This is going to be appropriate, for instance, if you're starting into a college level calculus class, but your high school trig is a little bit rusty. Trigonometry is really just the study of triangles, or trigons. And it's all based on the fact that the corresponding sides of similar triangles, that is, triangles that have identical angles, have lengths in a common ratio. That's all a lot clearer when we have a picture. So, here are a couple of similar triangles. Corresponding angles are colored identically. With the sides as labeled, A over C equals B over D. Or, to say it slightly differently, A over B equals C over D. So the corresponding sides in the left triangle have the same ratio as the corresponding sides on the triangle on the right there. Of course, the angles of any triangle have to add up to 180 degrees, or pi radians. So if we're talking about right triangles, the ratios of the side lengths are completely determined as soon as we specify just one other angle. So here's a couple more similar triangles, this time right triangles. And I've labeled the angle in the lower left of each one with theta. The sides now are labeled O, A, and H. Those are traditional pieces of terminology, traditional labels. They stand for opposite, adjacent, and hypotenuse. Those are completely universal in any trig book and most trig videos that you'll see here on YouTube. Now, once we've specified theta, the ratio O over H is going to be the same for this triangle, for either of these triangles, and in fact for any similar triangle with these angles. The same can be said for A over H, O over A, and so on. 6 ratios in total. Each one of these depends completely on theta, and so we can view each of these ratios as a function of theta. These functions, these trig ratios, come up so often that we give each one of the 6 trig ratios its own name. These are the fundamental trigonometric functions. Sine of theta is defined to be the opposite over the hypotenuse. Cosine of theta is the adjacent over the hypotenuse, and so on for tangent, cosecant, secant, and cotangent of theta. Of those 6 trig functions, the first 3, sine, cosine, and tangent, are by far the most common and the most important to remember. The other 3 are just the reciprocals. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite, for instance. Fortunately, there's a good mnemonic to help you remember these definitions. SOHCAHTOA. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. And tangent, opposite over adjacent. Okay, let's do an example. Here's a triangle with 2 sides and 1 angle labeled. We want to find all 6 trig ratios for the angle theta that I've labeled. So 2 of these we can do immediately. We know the hypotenuse, we know the adjacent, so we can do the cosine, the adjacent over hypotenuse, 12/13, and we can do the secant, the reciprocal of that, hypotenuse over adjacent, 13/12. In order to get the other 4 trig ratios, we're going to need to find the length of that opposite side. And we're going to do that using our old friend, the Pythagorean theorem, which comes up all the time in trigonometry. So a squared plus b squared equals c squared, or to say it differently, adjacent squared plus opposite squared equals hypotenuse squared. So let's label that opposite side with a b, and then write down our Pythagorean theorem. 12 squared plus b squared equals 13 squared. So b squared is 25, and since b has to be positive because it's a side length, b has to be 5. Now we're able to write down our other 4 trig ratios since we have the opposite labeled. Sine of theta, opposite over hypotenuse, is 5/13. Tangent theta, opposite over adjacent, is 5/12. Cosecant theta, hypotenuse over opposite, is 13/5. And cotangent theta, adjacent over opposite, is 12/5. Now, the value of the sine of theta depends on which angle we actually label on our triangle. If we label a different angle, we're going to get a different value for that sine, or for any other trig function. So, for instance, with this triangle as labeled, the sine of the angle in the lower left is b over c, while the sine of the angle on the upper right is a over c. Because when I change my focus from one of those angles to the other, I swap the roles of opposite and adjacent. In fact, the sine of the lower left angle is the same as the cosine of the upper right angle, and vice versa. In fact, in any right triangle, the two non-right angles add up to pi over 2. So if one of the angles is labeled theta, the other can always be labeled pi over 2 minus theta. And using what we have in the previous slide, we can relate the sine or cosine of one of the angles to the cosine or sine of the other. Similarly for secant and cosecant, and tangent and cotangent. In each case, we're just reversing the roles of the opposite and adjacent. This gives us 6 cofunction identities. The sine of theta is the cosine of pi over 2 minus theta. The cosine of theta is the sine of pi over 2 minus theta, and so on. In each case, we're just using the fact that we can change our perspective on the triangle, label the other angle instead of theta, pi over 2 minus theta. Now, there are many, many other trigonometric identities that involve these 6 trig functions. I'm just going to run through the very most basic, the very most important. First of all are some that we've already mentioned, the reciprocal identities. For instance, cosecant of theta is 1 over sine theta, and sine theta is 1 over cosecant of theta. There are some very fundamental identities for tangent and cotangent. We can write each of those functions just in terms of sine and cosine using these so-called quotient identities. Tangent of theta is sine theta over cosine theta, and cotangent theta is cosine theta over sine theta. You can check that each of those are true just by writing sine and cosine in terms of opposite, hypotenuse, and adjacent, and seeing the simplification that falls out. Finally, let's mention one other very, very important one, the Pythagorean identity. Now, I mentioned the Pythagorean theorem earlier, a squared plus b squared equals c squared. This one is directly derived from that. Sine squared theta plus cosine squared theta equals 1. This would be opposite over hypotenuse squared plus adjacent over hypotenuse squared equals 1. All of that simplifies to opposite squared plus adjacent squared equals 1. By the way, there are 2 other Pythagorean identities. They look like tangent squared theta plus 1 equals secant squared theta. Those come up sometimes, but not as often as this one, which is by far the most important. If you're looking to, if you need to use more sophisticated trig identities, I recommend just going to the Wikipedia page for trigonometric functions. There's an entire long list of those. Probably got just about everything you need.